We'll now look at a sequentially consistent machine with cache memories. And firstly, we can obviously not expect that caches somehow would make the machine support sequential consistency. It's the opposite. If we have a superscalar machine, one which can execute multiple instructions at the same time, including speculatively, and there are two read instructions, and according to the program order, the first one, one of them must be first according to the machine code and source code. And if that one misses, and the second one hits in the cache, then it may be very tempting to read the value that was available for the second read, but that is not permitted. Instead, the program order of all memory accesses should be maintained. That means even if there is a subsequent read cache hit, it must not be allowed to precede a previous read miss. They must be done one at a time. Otherwise, we don't have sequential consistency. Another issue is that if there are multiple CPUs that have accessed a variable, then there can be multiple copies of that variable. And if one of the CPUs all of a sudden wants to modify that variable, there must be some form of control which makes it, only one of them should be allowed to modify the variable at a time. Okay, and there is a mechanism which is called the cache coherence protocol. Okay, you can think of it as an akka program. So the cache and the memory controller, there will be many memory controllers for different parts of the memory, but they will sit and wait for messages. And the CPU will initiate the messages from the cache, such as when it wants to read, it will request the data, and the cache will send a message to the memory, okay, and it will reply with another message that contains the data. And when it wants to write, it will send a message that says that it wants to write. Okay, I will explain. There are two options, main options for doing the writes, and we can look at them right away. But there are three main tasks for the cache coherence protocol. First, at the write, the cache coherence protocol should make sure that there is only one copy of the data. And it can do that, only one copy of a certain variable. Okay, and it can do that either by removing all the other copies, the copies, the other ones, other than the one that is being modified, or it can send updates to the caches which have a copy, and to memory as well, of course. If in the future some CPU that did not have a copy also wanted the copy, it should get it from the memory and not from another cache, since it doesn't know which caches have a copy. Okay, so these two main approaches are called a write invalidate protocol or write update protocol. Before, there was a clear consensus of how to make easily programmable and fast multicores, it was not completely determined which of these two protocols are best. And there were machines sold with the right update from digital equipment, for instance, and they don't exist any longer. But it was not due to their choice of update protocol. Okay. But what it does is to send messages to the caches which have ever had a copy of a variable. And they continue to do that despite the program not being interested in updates any longer. So one could see it as the writing CPU is spamming the other caches. And okay, what's bad with that? Well, the main problem with this is that the network which connects the different CPUs and memories and caches, well, the caches and CPUs are at the same place. It will be overloaded with messages that really have no purpose. That's the main problem. There is another problem, namely that it is more complicated to implement sequential consistency with write update protocols. It has to be done in 2 steps, and we will not go into the details of that. Instead, we will just note that write update protocols are not as good as write invalidate protocols. But it is not the case that the engineers at Digital Equipment and other companies didn't measure and determine that it could be a good idea to use the write update. Obviously they did, but for the majority of applications that customers actually wanted to use these machines for, it turned out that write invalidate is more suitable. Okay, so that's the first issue. What to do when a CPU wants to modify a variable. The second thing is to detect when a write has completed. Okay, and why? Well, in sequential consistency, the CPU which does the write is not allowed to start another memory access instruction before the write has completed. Okay, so therefore we must define what is meant by completed. By completed is meant that no other CPU can read the old value. If no one has any risk of reading the old value, then we can agree that that write has completed. Okay, and we will see soon how that is done. And next, we must also maintain the illusion of atomicity. So if we have this chess-looking big machine with 64 nodes and different times for communicating between different nodes, depending on, of course, how close they are to each other and how much other activity is happening on the communication links in that part of the machine. Then there will be overlapping accesses, but the machine must behave as if they are not. Okay, so okay, about the cache coherence protocols. Of course, machines which are using relaxed memory models, they obviously also need some kind of mechanism, and they also use cache coherence protocols. But there, some of the rules are relaxed, and there are others which are added.